Today's computers are called classical computers because they operate based on the laws of classical physics, the branch of physics that sprung from Isaac Newton in the 1600s and includes Maxwell's equations for electromagnetism. Any computing device that you've ever used has been a classical information processor, from your phone to your calculator to the device you're watching this video on. In this first video, we'll talk about how classical computers store and process information, since later, this will help us discover how a new type of computing, quantum computing, stores and processes information. Let's begin. Today, our computers might look like this, and the information that they store is in the form of zeros and ones. This is their language. A sequence of zeros and ones may represent a letter or a sentence or a number in a computer. Now, we know that computers can store lots of information, but the simplest piece of information that a computer can store is called a bit. A bit is either a 0 or a 1, and bit is short for binary digit because of the two possible states, 0 and 1. And we can use Mr. Bit here to represent each of these states. When Mr. Bit is standing, he's in the 0 state, and when he is upside down, he is in the 1 state. Now, in a computer, if we're starting with Mr. Bit in the 0 state, we have the option to either do nothing and leave him standing up, or we can flip him. Now he's in a different state. He is upside down. The key here is that we've changed the information that is stored in the bit. When Mr. Bit is in the 0 state, he is storing a piece of information, the fact that he is upwards. When he is in the 1 state, he now stores information about the fact that he is facing downwards. And we can go back and forth between these two states. In classical computers, we use something called a logic gate to change the state of a bit. Given an input state, we operate on it with a gate and produce an output state. And in doing so, we are changing the information that is stored in the bit. This is how we process information in a computer. For example, this is the symbol of one type of gate called the NOT gate. The NOT gate takes an input of 1 bit and flips it to become the opposite state. So if we are starting with an input of 0, the NOT gate will produce an output of 1. This is the bit flip that we were just talking about. We've used this gate to change the information stored in a bit. However, the NOT gate can only operate on 1 bit, and we can't do much with just 1 bit of information in a computer. So how can we process more information? Well, let's increase the number of bits to 2. Now we have 2 bits that can both be in the 0 or the 1 states. And these 2 bits make something called a system. So now that we have 2 bits, we can do more bit flips. Yay! If we start with 2 bits that are both 0, we can keep the first one the same and flip the second, or we can flip the first bit and keep the second one the same, or we can flip both. Notice that now we have 4 possible combinations of bits. We started with 2 bits, and because we could flip each one, we have increased the number of possible states of our system. So because we have more states, we can represent more information. Generally, we can say that the number of possible states of the system will be 2 to the n, where n is the number of bits. Here we had 2 bits, so we have 2 to the 2, or 4 possible states. But how do we put these bits to use in a computer? Well, just like we used a gate to operate on 1 bit before, now we can design gates that operate on 2 bits. For example, this is the symbol for the AND logic gate. The AND gate takes a 2-bit input and produces a 1-bit output. If both bits are 1, then it produces a 1. Otherwise, it produces a 0. Let's look at an example. Say that we start with 2 0 bits as inputs. What will the output be? Well, the AND gate only produces a 1 when both of the inputs are 1. And since they are not both 1 in this case, then the output will be a 0. If the input is a 0 and a 1, or a 1 and a 0, the output is still a 0. But if the inputs are 1 and 1, then the output will also be a 1. We can represent these results in a truth table, where we indicate the corresponding input states, A and B, and the corresponding output state, C. The truth table tells us what output the AND gate will produce, given 2 inputs. It's called a truth table because sometimes people refer to the 1 state as true and the 0 as false. So it tells us when the outputs would be true or false. There are many other types of gates that a classical computer can use to process information. A second one is the OR gate, which outputs a 1 only if one of the inputs that it receives is also a 1. If the inputs are 0, 0, the OR gate produces a 0 state. If the inputs are 0, 1, however, the gate produces a 1 state because at least one of the inputs is a 1. The inputs 1 and 1 would also produce a 1 for the same reason. Our last gate example is the XOR gate, sometimes called the exclusive OR gate, which differs slightly from the previous OR gate. The XOR gate outputs a 1 if one input bit is 0 and the other input bit is 1. If both input bits are 1, then the XOR gate outputs a 0. For example, if both inputs are 0, the output would still be 0. If one of the input bits is 1, then now we would get the output of 1 as well. However, if both of the inputs are 1, then the output is 0. All of these are examples of Boolean gates. A Boolean function is one that operates on binary elements, zeros and ones, and there are other Boolean gates that are useful in computations too. Now, the output of one gate can be used as an input to another gate. A sequence of gate operations forms a logic circuit. A logic circuit is what a computer program tells the computer to do. To execute a set of Boolean operations and produce an output that is the solution to a problem of interest. In a higher level, more abstract sense, this sequence of operations is referred to as an algorithm, a set of instructions designed to perform a particular computational task. A task might be producing an image on your screen, finding the numerical solution to an equation, or simulating a physics problem, or loading a web page, or you get the idea. There are zillions of possible tasks we can program a computer to do, and it is all based on these simple Boolean gates. So now that we know how to process information theoretically with the fictional Mr. Bit, we can ask, how are bits realized physically? In computers, we have electrical components called capacitors, which store energy. These capacitors are our real-life Mr. Bits. When a capacitor is full of energy, it is in the 1 state. When it is empty of energy, it is in the 0 state. That's one way to store information in the computer. There are other ways, but for the sake of simplicity, we'll just think of this capacitor model of a bit. There's another component of a computer called a transistor, which signals when to fill the capacitor or empty it. The transistor changes the state of the capacitor, meaning it changes the state of the bit. And transistors can switch quickly, on the timescale of microseconds, a millionth of a second. In combination, these transistors and capacitors physically implement the Boolean logic described previously, allowing us to store and process information in the computer. And in fact, there are millions or billions of these components on a single computer chip, so a very large number of instructions can be carried out every second. More specifically, when a transistor signals to change the state of the capacitor, it uses an electrical current. A current is made up of flowing electrons, these cute little guys over here. And when the current passes through a transistor to the capacitor, it changes the state of the capacitor. The current changes the state of a bit from being 0 to 1, or 1 to 0. It's a real-life implementation of a gate. And that's it for the fundamental workings of a classical computer. And so now we've gone over classical information processing that is used in all of today's computers. We learned that bits can be physically implemented by capacitors, and they can store information in the form of two possible states, 0 and 1. Though we can't do much with one bit of information, so we use many bits to store enough information to carry out useful tasks. And we can change the information stored in these bits or process information using operations called logic gates, which are transistors and currents in computers. With these concepts, we are now able to expand from classical information processing to quantum information processing that is used in quantum computers. Tune into the next video to find out how we can make this exciting leap with the help of our friend, quantum physics. This video was written, narrated, designed, and musically composed by Romi Lifshitz. Thank you so much to Professor Jonathan Baugh from the University of Waterloo's Institute for Quantum Computing for his immense support in making this video. The Baugh Lab is working on exciting physical devices that will enable quantum information processing. To learn more about their amazing work, be sure to check out the link in the description, and tune in to our next videos.